Acme Toy Company prints baseball cards. The company claims that 30% of the cards are rookie cards, 60% are veterans, and 10% are all-stars. Suppose a random sample has the following cards. Test Acme's claim that the distribution is a good fit with the prints of baseball cards at a alpha equals 0.05 level of significance. So this type of problem is a goodness of fit chi-square test. And the reason why I know that is because they give me a list of percentages for a categorical variable. So, and they ask if it fits the distribution. So here are the percent. Now, with this problem, we're going to need to know these expected frequencies. And so we have to first do like this pre-problem is we write out the percentages. So the categories are rookies, veterans, and all-stars. And the percentages that belong to each of these categories, they say the company claims that 30% of the cards are rookies. So this is 30%. The veterans, 60% are veterans, 60% are veterans, and 10% are all-stars. Now to find the expected values, you just multiply the number that is going to be sampled times by the percentage. So they say, all right, and then this one's a little bit tricky because they don't tell you how many are sampled, but they do tell you how many are observed in each category. So we know if we add up all of these, 25 plus 110 plus 15, then we can find out how many people were sampled. I don't really like that. I feel like they're being a little bit tricky here. They should have just given us how many people are sampled. So quickly, I have to add that together. So 25 plus 110 plus 15 equals 150. So our N here is 150. So all we have to do is multiply the percent down. So 150 times 30%. Let me just erase this because honest. 30% written as a decimal is 0.30. And then we do 150 times 60%, so it would be 0.60. Well, the zero doesn't matter, that 150 times 10%, 0.10. And now I multiply these across. And I have to find my calculator down here. Okay. So 150, I do this quickly on a calculator, times 0.3, 45. I'm going to do this 150 times 0.6. That's going to be 90, and then 150 times 0.1, 15. So it's 90 and 15. There we go. Okay, stop this aside. Okay, we could just double check to make sure we did that correctly. Those should add as well to 150, and they do. Okay, that looks good. So now those are the answers that go in here. So this expected value for the rookies is 45. This is 90, and this is 15. Now we're actually ready to do this chi-square test. The thinking behind this test is if these do in fact fit this distribution, meaning that 30% of the cards, roughly 30% of the cards are rookies, and 60% of the cards are veterans, and 10% are all-stars, then the observed frequency, which we actually observed in the sample, is going to be similar to the expected frequency. And if we subtract these, we're going to get a very small value because of how closely observed and affected are. The larger these differences are, the more it is against the null hypothesis. The null hypothesis here, just a reminder, the null hypothesis is the thing that we assume to be true. And that's what we assume to be, that the distribution was correct when we calculated these expected frequencies. So the null hypothesis is that the random variable follows the given distribution, namely 30, 60, and 10%. 30%. That rookies, I'm not going to write all of it out, but 60% and 10%. Okay. And the alternative hypotheses would be it does not follow. If those differences are large, we will be able to say that it does not follow that distribution. And what we're really doing when we do this chi-square test, the chi-square distribution is kind of a right tailed distribution, or right skewed distribution. So the further out into this tail, the larger, this is all positive. So the larger these differences are, the further out in the tail that it will be, and the smaller this p-value will be. And so the smaller that p-value is, then the more evidence it is against the null hypothesis that it does follow that distribution. So let's go ahead and find out what that p-value is and what the test statistic is. So we can enter in, we go stats, and we go to tests, and we're going to a goodness of fit test. So, first I have to go to stat edit, and I have to we're going to clear out all of this information from a previous problem. And for some reason, it did not do a good job of clearing for me. And now it doesn't want to. Okay. I'm going to put everything, the observed frequencies here in my first one. Okay, then in my second one, it's 5, 90, and 15. Right, then now I'm ready to go to stat and tests and goodness of fit test. D, the chi-square goodness of fit, GOF test. So I just have to make sure, did I put my observed in the first column? I believe I did, because I did it exactly the way this table looks. So I did in fact put my first column was in L1 and it is the observed, so that's good. And my expected were in L2. That's how I put it into my calculator, so that looks good as well. The degrees of freedom is the number of different categories. So we have, you can see from this problem, it says category at the top here. It says category, so we have 1, 2, 3 different categories. So the degrees of freedom df is equal to k, which is the number of categories, minus 1. So it's 3 minus 1, which is 2. So we're going to put 2 in here. And now we just press calculate. So now we can see our chi-square value is 13.3. So this distance along the x-axis, it's 13.3. So you can see it's kind of far down. In my opinion, that's kind of far from this is 0 over here, and so that's 13.3. Then it's saying the p-value is 0.001 to the area underneath the curve to the right. This type of goodness of fit is always a right tail test. You're always looking at the area under the curve to the right of the chi-square value. So that is 0.00127. And so let's enter in all these. Let's just double check all our answers here. This should have been 13.3, and it is. And then this should be 2, which it is. And then it should be the 0.003. So they rounded this 0.00. I had 0.00127, but they rounded it to 4 decimal places, adding 1 to the 2. So it became 0.0013. Is the p-value less than alpha? So we have to ask, is the p-value less than alpha? So is the p-value, which is 0.0013, is it less than alpha, which in this case, alpha is 0.05? And I would say, yes, it is less than alpha. So this answer here is yes, and we'll see. This is yes. Then, because the p-value is less than alpha, we will reject the null hypothesis. And because we reject the null hypothesis, so the good thing I've written them out over here, the null hypothesis was the variable follows the distribution. So if we're rejecting that, that means the variable does not follow a distribution. So we're going to say there is sufficient evidence to support the claim that the Acme's distribution of baseball cards. Well, we don't want to say it's a good fit because we're going to say there is not. This is weird because you normally would say there is sufficient evidence, but they actually have written here there is sufficient evidence for the alternative hypothesis, which is that baseball cards. They're actually saying there is sufficient evidence for the null hypothesis, which is not what we want to say. And they're saying there is not sufficient evidence to support the distribution of baseball cards as a good fit. So this is, this is actually the first one is what we really want. All right, so I do want to say that this one is a little bit, I don't like the way they've worded it in this final conclusion. What they should have said is there is sufficient evidence to say that, wait, Here, hold on. We reject the null hypothesis. So we reject the fact that the distribution, the variable follows this distribution. So we should say there is sufficient evidence to show that the variable, does not follow the distribution. That's what we should have. That's how probably a better way that I would have worded this final conclusion. But we just want to say that the variable does not fit the distribution. So the one that says that is actually this top sentence. So the answer is there's not. So just ignore the part that it says is not sufficient evidence. Just focus on the evidence here. It says that we're not claiming that it's a good fit to the distribution, which is exactly what we said. When we reject the null hypothesis, we're saying it's not fitting the distribution, that's what we want to say. So I apologize because normally, whenever we reject the null hypothesis, the wording is always there is sufficient evidence. I'm sorry. Whenever we reject the null hypothesis, I always like to word my conclusion in there is sufficient evidence. However, they're being tricky here with the way they've worded these final ones. And they are asking us to look a little deeper into the understanding of actually these sentences. And they want us to find the one that would match. So we would match rejecting the null hypothesis and accepting the alternative hypothesis as truth. So the statement here that says that the variable does not follow the distribution is actually the first statement. All right. Well, I hope that this made sense. I apologize for the tricky part in part G there, but have a great day.